August 3rd, 1944. Past midnight, the fighting over the hedgerows west of St. Lo still flickers like distant lightning. Tracers cut through the darkness. Somewhere in that chaos, a P-47 from the 362nd Fighter Group tears the tail off a low-flying Focke-Wulf. The German pilot, cool under pressure, cuts his power and slides the crippled fighter into a ditch. Then he disappears into the dark bocage before anyone can reach him. At first light, a patrol from the 30th Infantry Division stumbles on the wreck and radios it in to 9th Air Force. No fire, no holes in the engine cowling, and most importantly, the thing everybody wants is still sitting there, intact. By noon, mechanics are already working. They pull the detachable nose ring, revealing a WW2 radial engine. It doesn't look like anything a mechanic from Newark or Wichita has ever seen up close. On the left side of the case, there's a stubby throttle quadrant leading into a mysterious box about the size of a lunch pail. Its nameplate is stamped in Gothic letters, Commando Jarrett. The sergeant from the recovery team lets out a low whistle. Never seen a single lever set up on a fighter, he mutters. Then he stops talking and starts unbolting. Orders are crystal clear. Crate the whole power plant and ship it out before some artillery crew decides to use it for target practice. 3 weeks later, the engine arrives at Wright Field in Dayton, Ohio, home of the Air Technical Service Command. It shows up on a flatbed truck with mud still packed into its cooling fins. Dr. Arthur McKendry, a 35-year-old combustion specialist borrowed from NACA's brand new lab in Cleveland, runs his hand along the BMW's pushrod housings. Then he points at that mystery box mounted under the throttle. That thing, he tells his team, is either German superstition or the reason our pilots keep saying a Focke-Wulf goes from idle to climb power in one heartbeat without missing a beat. All summer long, American pilots have been sending the same report from over Normandy and the Falaise Pocket. The WW190s jump like scalded cats at low altitude. They don't flood. They don't foul their plugs when the pilot slams the throttle. They run glass smooth even when the pilot yanks the stick and throws the airplane into a vertical roll. The P-47s and P-51s, sure, they can do the same thing, if the pilot is absolutely perfect. He's got to nurse the mixture, watch the prop, manage the supercharger, monitor the boost, and finesse the throttle like a church organist on Sunday morning. One mistake, and that Pratt & Whitney will cough, or that Packard-built Merlin will start pinging on bad fuel. The Germans, one lever. Push it forward to go faster. Pull it back to stay alive. McKendry signs out a test cell. They mount the 801D on a stand, hook it up with American gauges, and wire that mysterious box exactly as they found it. No German manuals, no parts list, no helpful BMW foreman who speaks English, just mechanics, with wrenches and a scientist who thinks in pressure ratios and cam profiles. The plan is straightforward. Map the throttle response, manifold pressure, prop pitch, mixture, and supercharger gear selection, from idle all the way to war emergency power, and back again. Then tear down that box and see what kind of satanic watchmaking is driving it. First run, August 29th. They're using US 100-130 avgas cut down to German specifications. American oil, Ohio heat. McKendry gives the cell chief a nod. The starter spins. The 801 coughs twice and roars to life with a bark that rattles the observation glass. At 1200 RPM, every needle sits rock steady. McKendry signals with 2 fingers. Advance the throttle 1 inch. The operator pushes. Manifold pressure climbs. Prop pitch follows right behind it. The mixture leans, then richens automatically as the RPM builds. No knock, no hesitation. That single lever is controlling all 3 systems with something that feels almost uncanny, like anticipation. They try a fast slam to takeoff power. The prop governor and supercharger shift in perfect unison. The engine howls clean and strong. McKendry scribbles notes on his clipboard, and he can't help himself. He laughs out loud. Across the catwalk, a captain from Material Command stands watching, arms crossed. "We thought the secret would be their fuel injection system," he says. McKendry shakes his head and taps the black box with the back of his pencil. "No, the secret's right there. It's not in the fuel. It's in the control." 2 days later, the BMW 801 sits in pieces across a dozen stainless steel benches inside Wright Field's Engine Test Building 23. The Germans built this thing like a mechanical cathedral, every part carefully numbered, every fastener drilled for lock wire. McKendry's team labels each sub-assembly: compressor impeller, reduction gear, oil pump cluster, ignition ring. But everyone keeps coming back to that squat aluminum block bolted to the throttle pedestal, the commando jurat. Nobody knows quite what it does yet. They only know what it achieves: throttle, propeller pitch, mixture, and supercharger shift, all governed by one-hand movement. The Americans start calling it the command box, but McKendry refuses the nickname. "It's not a box," he says quietly. "It's a brain." He removes the cover. Inside, there's nothing electronic. No wires, no resistors, no vacuum tubes, just gears, dozens of them. Tiny helical pinions, worm drives, cams, and spring-loaded levers, all working in impossible harmony. It's a mechanical computer, executed in brass and steel, smaller than a shoebox, but somehow capable of managing 4 power systems simultaneously. The workmanship borders on insane. Each cam face is ground mirror smooth and etched with curves that change along its axis. McKendry picks one up, turning it in the light. "These aren't circles," he says. "They're equations. Here's how it works. When the throttle shaft rotates, it turns a bis R, single master cam. That cam moves 3 different followers, each one translating rotation into motion for separate linkages. One controls the propeller governor, another handles the mixture, the third manages the supercharger clutch. But the cam profiles aren't simple curves, they're non-linear. Near idle, they move gently, barely adjusting prop pitch. Past 40% throttle travel, they ramp up aggressively, enriching fuel flow and advancing ignition timing before the pilot ever feels the torque surge building. Everything happens slightly early. It's as if the device predicts what the engine will need. McKendry traces the fuel circuit next. The BMW 801 doesn't use carburetors like American engines. It uses a mechanical injection pump driven by a cam ring, metering fuel directly to each cylinder. The American Pratt & Whitney R2800 runs fine on carburetors most of the time, but they stumble under negative Gs or violent maneuvers. The BMW's pump doesn't care about attitude or orientation. It just works. The commando jurat feeds it a continuously variable signal. Turn that single lever, and injection rate, ignition timing, and prop pitch all change together, keeping the engine at its optimal torque curve through the entire flight envelope. It's predictive load control, a concept that won't show up in Detroit for another 20 years. The Germans didn't invent this out of luxury or excess. They built it out of pure necessity. By late in the war, Luftwaffe pilots were dying faster than training schools could replace them. Complex engine management was killing more rookie pilots than enemy gunfire. So BMW's engineers in Munich made a decision: design an engine that could think for the pilot. The Commando Garret didn't just simplify the cockpit, it equalized skill levels. A novice pilot could jam that throttle forward and still get smooth power delivery, automatic mixture correction, optimal boost pressure, and a propeller that never oversped. McKendry jots notes in the margin of his report. System minimizes pilot error. Combines 4 separate controls into one input. Functionally, a closed-loop mechanical controller, equivalent to automatic boost regulator, plus prop governor, plus carburetor, mixture compensator, plus turbo clutch logic, all mechanical. No electronics required. He takes the cams down to the metallurgical lab for hardness testing. The case depth is perfect. Tolerance variation, less than 0.002 of an inch. Even the spring steel is polished to a mirror finish. The Americans can make precise parts when they need to, but this is something different. This is watchmaking at an industrial scale. The Germans spent man-hours, like water, to eliminate every microsecond of lag. By September, the first engineering report starts circulating through NACA and Pratt & Whitney. The title is dry and technical. Preliminary Technical Analysis of the BMW 801D2 Power Plant. But the summary line reads like an accusation. Engine performance. Superiority derives not from raw power output, but from integrated control coordination. System intelligence resides in mechanical logic unit, not combustion chemistry. When McKendry's commanding officer reads that sentence, he circles it in red pencil. "You're telling me," he says slowly, "that the secret wasn't higher octane fuel, or fuel injection, or better metallurgy. It was gears." McKendry nods once. "Gears," he confirms, "but gears that think." October 9th, 1944. Wrightfield's test stand is running again. This time, the BMW 801 is hooked up to American instruments, calibrated to within 1/10 of an inch of mercury. McKendry's goal now is to quantify what intuition already knows, to prove, in hard data, what every pilot over France has felt in his gut. He starts the run at idle. 1,000 RPM, manifold pressure at 27 inches. One smooth motion of that single throttle lever. No separate prop lever, no mixture knob, no boost control. The engine answers instantly. The fuel flow curve rises in a perfect parabola. The propeller governor responds within 2 seconds. The supercharger clutch engages automatically at 1,900 RPM. Manifold pressure stabilizes at 44 inches. It's absolutely perfect. The Americans run the same test with a stripped-down R2800 from a P-47. To match the German engine's response, a test pilot has to manipulate 4 separate levers in exact sequence: throttle, mixture, prop pitch, and turbo wastegate. It takes training, finesse, and more than a little luck. Get the order wrong, and you'll get a cough or detonation. McKendry watches from the control booth. "We build engines," he says quietly. "They built a system. The data tells the whole story. Time from idle to full takeoff power. BMW 801, 3.2 seconds. R2800, 8.5 seconds. Manifold pressure overshoot. BMW, 0. R2800, 11%. RPM undershoot during throttle slam. BMW, 0%. R2800, 9%. No electronic control. No vacuum servos. Just gears and cams." McKendry shakes his head, genuinely marveling at the precision. "They built feedback loops," he says, "out of metal." He dismantles the supercharger clutch housing next, and inside he finds another surprise: a hydraulic servo driven by engine oil pressure. It shifts automatically between low and high supercharger gear when altitude and manifold pressure intersect a specific curve, a curve that's encoded right into the Commando Girat's cam profile. The result? No power lag at 15,000 feet, no shock loading on the gear teeth, no human timing errors. It's not magic. It's the world's first fully integrated mechanical engine management system. The Allies have been focusing on raw horsepower. Pratt & Whitney's Double Wasp, Rolls-Royce's Merlin 66, Wright's Cyclone. All incredible engines. But every one of them depends on pilot finesse to extract their full potential. The BMW's real strength isn't in its combustion chambers, it's in its control architecture. The field notes start filling up with comments from visiting engineers. One guy from Infantry Division writes, "This unit anticipates load. In automotive terms, it's an analog computer translating driver, intent into optimal combustion state." McKendry's only response, underlined in ink, "Exactly." The report spreads to NITA's Cleveland lab, then over to Pratt & Whitney's design office in Hartford. Engineers who've spent years chasing better throttle response through improved carburetors stare at the cutaway drawings and realize they've been looking in completely the wrong place. The Germans didn't fix the mixture problem. They removed the pilot from the equation entirely. And then comes the next surprise. not in the cam profiles themselves, but in the materials. When the metallurgists etch samples of the Commando Jurat's internal gears under acid, they find them case-hardened in a salt bath rather than gas carburized. Uniform case depth of 0.7 millimeters. No surface cracks. No inclusions. The precision is too fine for mass production. Each unit was hand-ground to final tolerance. One gear in particular catches everyone's attention: a stepped pinion coupling throttle motion to mixture correction. It has tooth geometry that actually varies across its width. That means the system's mechanical ratio changes dynamically as it rotates. The geometry itself is encoding a performance curve. It's a mechanical algorithm. When McKendry shows it to a liaison from Pratt & Whitney, the man just stares for a long moment. Finally, he mutters, "Jesus Christ, they were programming engines." Within a week, Army Air Forces headquarters cables the full analysis to Freeman Field, Indiana, where captured German aircraft are being assembled for flight evaluation. One of the test pilots, Major Fred Borsodi, takes a restored Focke-Wulf up with the original engine. His report comes back in late October. Engine control is exceptional. Single lever makes power handling idiot-proof. Immediate throttle response with no detonation whatsoever. Automatic altitude compensation is smooth as silk, equivalent to turbo control logic without any pilot input required. In dogfight maneuvering, the advantage is evident. McKendry reads it twice, then turns to his team. "There's our proof," he says quietly. "The engine doesn't make more power than ours. It just uses all of it." The next challenge becomes obvious. Replicate it, or better yet, surpass it, without needing the man-hours of a precision watch factory. The Americans can't afford 50 hours of hand-fitting per unit. They need mass production, field repairability, and materials that a plant in Detroit can stamp out at speed. McKendry's notes begin to shift from pure analysis to synthesis. He starts sketching simplified linkages, hydraulic governors, electric servos. The future isn't the Commando Jurat itself, it's what comes after it. The Germans built genius into brass and steel. McKendry intends to translate it into voltage and wire. November 12, 1944. The cold wind. Off Lake Erie cuts straight through the hangars at NACA's Aircraft Engine Research Laboratory in Cleveland. The BMW 801 has been crated up, shipped north from Wright Field, and mounted in a dynamometer cell right beside a gleaming American R2800. 2 engines, same displacement, same output class. One built by the richest industrial machine on Earth, the other built by a nation being systematically bombed into rubble. And yet, somehow, the German design runs smoother, cooler, and cleaner. Dr. Arthur McKendry stands on the observation catwalk, clipboard tucked under one arm, a cigarette burning down between his fingers. Below him, technicians warm up the radial with practiced ease. The Commando Jurat remains bolted to its throttle pedestal, a spiderweb of linkages radiating out from its casing like arteries from a beating heart. McKendry isn't here to marvel anymore. He's here to dissect the logic and turn it into something the United States can build by the thousand. The question driving this next phase isn't how it works. Everyone understands that now. The real question is why it was built this way in the first place. The NACA team discovers that the Commando Jurat evolved from bomber engine governor systems that BMW's Precision Division had built before the war. The Germans simply extended the principle, connecting every critical parameter, fuel flow, manifold pressure, prop pitch, even magneto timing, into a single predictive feedback loop. But the rationale behind it wasn't just about performance, it was about pilot survival. German training hours had plummeted since 1943. Rookie pilots were showing up at the front with less than 100 hours of total flight time. Meanwhile, a P-51 pilot trained in Florida or Texas had 300 hours minimum. The Commando Jurat closed that gap, not by training the man better, but by mechanizing his judgment. The engine became the instructor, the brain, the reflex. McKendry captures it perfectly in a lab memo. They automated competence. The Americans, on the other hand, still rely entirely on pilot finesse. Every throttle movement demands a mental checklist. Throttle first, mixture second, prop pitch third. Misjudge that order, and an R-2800 can cough itself straight into detonation. American pilots train through it until it becomes second nature. German engineers designed around it completely. To translate the device into American production, McKendry teams up with General Electric's Automatic Control Division, the same engineers who built the turbo supercharger controllers for the B-17 Flying Fortress. Together, they take the Commando Jurat's mechanical logic and sketch out a pneumatic electrical analog. Instead of precision cams, they use pressure diaphragms. Instead of hand-fitted gears, they use resistors and servos. The goal: a unified engine control unit for piston fighters. A bridge between the mechanical present and an electronic future. By late November, the prototype actually works on BICE paper anyway. But in the meantime, another question rises to the surface. A political one. Can the Army Air Forces openly admit that the enemy solved a problem America never even defined? At a closed briefing in Washington, McKendry stands in front of a room full of generals and aircraft manufacturers, flanked by diagrams of torque curves and throttle angle graphs. He lays out the evidence in his usual clipped, matter-of-fact tone. Reduced pilot workload, consistent power output across all altitude bands, zero delay between throttle motion and actual torque rise, 17% improvement in climb rate under identical conditions. Then he delivers the line that makes everyone in that room fall completely silent. Gentlemen, the Germans didn't build a better engine. They built a better interface. A colonel from Materiel Command frowns. We already have superchargers and governors, he says. Why reinvent the wheel? McKendry clicks to the next slide. A graph shows engine torque plotted against time for both engines. The American curve wobbles noticeably, spiking high before leveling off. The German curve climbs smoothly, a single continuous line. That wobble right there, McKendry says, pointing with his pencil, is where pilots die. When the briefing ends, nobody applauds. They don't need to. Orders go out within the week to begin a limited trial program at Pratt & Whitney. They call it Project Gray Fox, an experiment in integrated power control using modified P-47 and P-61 engines. Back in Cleveland, the BMW 801 just keeps running. Engineers cycle it through hundreds of throttle sweeps, measure pressures, tear it down again, inspect for wear. Nothing breaks. The brass cams show no scoring whatsoever. The linkage tolerances hold within factory specification after 50 brutal hours of hard use. One technician writes in the daily log, "Feels like the damn thing knows what we're about to do." McKendry watches through the observation window and allows himself a thin smile. It does, he says. That's the whole point. By December, intelligence reports filtering back from Europe confirm the pattern repeatedly. Pilots from the 8th Air Force flying over Germany note that Focke-Wulfs and Doras can dive through severe turbulence without power surges. Their engines never overspeed, even in violent negative G dives. That single lever control lets them transition from a dive straight into a climb in one fluid motion. Allied pursuit pilots have to juggle 3 separate controls to do the same thing, losing precious seconds that simply can't be regained. In McKendry's mind, the implications reach far beyond this war. The piston engine's almost finished, he writes in a private note. But the lesson stands. Control will win the next one. Jet or piston, it doesn't matter. Whoever perfects automated control wins the sky. He doesn't know it yet, but engineers at General Electric are already drafting proposals for a jet engine control TWIS box modeled directly after his diagrams. Within a year, it will carry a new name, Electronic Engine Control Unit, and its ancestor, the one that started everything, still sits on his workbench, gears gleaming under harsh fluorescent light. The German word Kommandogerät stamped deep into its aluminum skin. January 15th, 1945. Wright Field, Ohio. Outside, winter snow drifts high against the hangar doors. Inside, a mock-up cockpit glows under yellow bulbs. A cut-down throttle quadrant sits mounted in front of a stripped P-47 fuselage shell. On it, a single lever, but this time, it's not connected to the original German cables. Instead, it's hooked to a tangled mess of American-made linkages, pressure valves, and relays. The first real attempt to replicate the Kommandogerät in U.S. hardware. McKendry's engineers call it Unit 1. The concept is simple. Translate German mechanical logic into something America can actually mass produce. The execution? Absolutely brutal. The Kommandogerät's precision cams can't be stamped out on a press. Its spring rates can't be matched with standard U.S. alloys without heat-treat distortion creeping in. The salt bath case hardening the Germans used is essentially banned in American machine shops. Too toxic, too slow, too labor-intensive. So the team replaces the elegant cams with hydraulic pistons and proportional valves driven by manifold pressure and oil flow. Compared to the German original, it looks crude, but it works. Mostly. They hook the prototype up to an R2800 on the test stand. Throttle response feels smooth. Prop pitch follows automatically. Mixture stays rich under load, lean during cruise. For 30 solid minutes, it seems absolutely flawless. Then a pressure diaphragm sticks. The engine stumbles hard, surges violently, and backfires straight through the intake. It nearly shakes itself clean off the test stand. McKendry slams the emergency kill switch. The entire lab goes dead silent, except for the tick-tick-tick of rapidly cooling metal. Too complicated, one of the techs mutters into the quiet. No, McKendry answers firmly. Not complicated enough. The Germans understood tolerances we don't even measure yet. He isn't exaggerating. In the original Kommandogerät, every single cam lobe transitions along 3 different radii, each one corresponding to throttle position, altitude, and RPM. The relationships are geometric poetry, mathematical functions literally embodied in hardened steel. The American copy, with its diaphragms and mechanical linkages, can mimic those curves reasonably well. But it can't predict them. The original doesn't wait for pressure to change and then react. It anticipates the change mechanically through overlapping cam tracks. It isn't just reactive, it's predictive. Over the next month, engineers at Pratt & Whitney and General Electric test variant after variant. Pneumatic controls, hydraulic boosters, even crude electrical servos driven by variable rheostats. None of them match the BMW's seamless integration. McKendry starts calling the problem mechanical intuition. The Germans achieved it through hand-fitted parts. Every single Kommandogerät is slightly different, each one individually tuned to its specific engine by a skilled technician with a file and a micrometer. Mass production kills that kind of artistry stone dead. By February, the test program has gained an official designation, Project Magister. Its stated objective? Reduce the Kommandogerät's complexity by 90% while keeping 95% of its actual function. They do it the American way. Simplify, modularize, quantify everything. McKendry splits the integrated system into 4 independent servos linked through a central manifold. One controls prop pitch, one handles mixture, one manages ignition timing, one regulates boost pressure. The levers remain unified under a single pilot input, but all that mechanical choreography disappears, replaced by straightforward proportional response curves. When Unit 3 finally runs properly, it behaves differently. It's not graceful like the German brain box, but it's obedient. Throttle motion translates cleanly into power without surging. The prop adjusts on its own. Mixture shifts automatically. Altitude compensation gets handled by a simple barometric capsule. The engine doesn't purr. It growls. But it obeys commands. McKendry watches it run and nods slowly. Good enough to mass produce, he says quietly. But theirs will always be smoother. Word of his progress spreads quickly up the chain of command. In March, representatives from Allison Packard and North American Aviation arrive at Wright Field for a formal demonstration. The chief test pilot, Major Ralph P. Jenkins, straps himself into the mock cockpit, pulls that single lever forward, and feels the engine behind the firewall respond instantly. Feels like a Merlin with manners, he jokes afterward. The data backs him up completely. Response time is within 6% of the German benchmark. Power stability at high altitude is actually even better, thanks to tighter American tolerances in the hydraulic lines. The briefing that follows is deliberately cautious. The U.S. version will not be a direct copy of the Commandojurat. It will learn from it, but chart its own path forward. McKendry writes the new doctrine himself. Our goal is not replication, but evolution. Integration of engine and propeller control under one lever is no longer a foreign idea. It's a tactical necessity. The next war will not permit a pilot to be a mechanic in the cockpit. In April, engineers begin sketching something even stranger, replacing mechanical cams entirely with electronic circuits. GE's servo group up in Schenectady starts experimenting with vacuum tube amplifiers connected to variable resistors, translating throttle voltage directly into servo motion. They call it electric engine coordination. It's clumsy, unstable. The whole assembly burns out after just 5 minutes of operation. McKendry watches the sparks fly and smiles anyway. That's the future right there, he says. Not springs, not cams, signals. Back in Europe, Focke-Wulfs are still fighting, but there are fewer of them every week. The Reich is collapsing, fuel depots bombed into craters, production lines shattered by daylight raids. Yet even as Allied armies overrun Germany itself, captured engineers confirm what McKendry already knows in his bones. The Commandojurat wasn't some exotic prototype or limited experiment. It was standard equipment on every BMW-powered fighter since 1942. The Germans had been flying with automatic engine management for years, while the Allies dismissed it as theoretically impossible. When U.S. technical teams finally enter Munich in May of 1945, they find the BMW plant still half intact. Blueprints of the Commandojurat hang on drafting boards, dusted white with plaster from bombed-out rafters overhead. A handwritten note in the margin of one drawing catches an intelligence officer's eye. He has it translated immediately. Für den neuen Strahltriebwerk, Prinzip bleibt gleich. For the new jet engine, the principle remains the same. McKendry reads that translation weeks later, and the truth hits him all at once. The Germans were already adapting the exact same control logic to jet turbines. Automatic fuel control, airflow scheduling, compressor bleed regulation, that mechanical brain that made a piston engine think was being reborn in steel fuel valves and precision nozzles for the Me-262 jet fighter. The war is ending, but the race to control power, to make machines think for their pilots, has only just begun.